Welcome to the second lecture on optimization and smoothing. Today we have three objectives building on the nonlinear least squares that we covered. We want to extend it to a class of problems that they do not necessarily deal with the least squares problem. If the objective function is not in the form of least squares, we want to learn what to do with it, and that will lead to a new algorithm called Iteratively reweighted least squares, IRLS. The second topic is about robust estimation, the class of M estimation. And the third topic is how to solve the optimization problem on manifold, and in particular on Lie groups. So let's review the nonlinear least squares problem. The objective function comes in the form of the norm squared of a residual. The residual was a map from the input Rn to a vector Rm. And the norm was the Euclidean norm. In this type of problem, the residual is not necessarily a linear or affine function, so we had to linearize. Knowing how to solve the linear least squares problem, the Gauss-Newton algorithm was telling us to linearize around the current guess at the current iteration, reconstruct an affine approximation of the nonlinear residual around the current guess, initially around x0. Therefore, the affine approximation, which is in the form of ax plus b, will have a constant part residual as a function of x0 plus a Jacobian matrix evaluated at x0 times a delta movement. We call it d here, or you could call it delta x. When we solve d, and then we integrate by adding it to the previous value, and then we continue until convergence. So that's the idea behind the Gauss-Newton algorithm and how to solve a nonlinear least squares problem. So we solve the linear problem many times by iterating. So this is a very common theme and idea. When the problem is nonlinear, linearize and iterate. So the algorithm is, in the basic form, is quite simple to implement. You write a loop. You might set a fixed number of iterations because you don't want your solver to go and optimize it forever. And the convergence is when, let's say, the norm of the Jacobian transpose times R is 0. That's a good condition. Why? Because the gradient of the objective function is Jacobian transpose R. So if the norm of the gradient is 0, we have satisfied the necessary condition. We can stop. We are at the optimal point. So this was the Gauss-Newton algorithm. One natural question that comes up is, what if the norm is not the Euclidean norm? Because depending on the problem or what you're after, you might choose not to define the objective function to use the Euclidean norm, and that's very common. The Euclidean norm was one type of norm that's very common, and we pointed out that you can call it L2 norm. In general, you can have P norm. We defined it last time that you raise each term to the power of P, you add them up, absolute value of each term, because if it's odd, you don't want to get negative value. And then you take you raise the sum to the power of 1 over P. That's the P norm. So we wish to minimize the objective function that is in the form of a p-norm, not 2-norm. And p-norm raised to the power of p to just minimize the sum. That will be equivalent of the same objective function. There's no reason to, again, raise it to the power of 1 over p. So this is no longer the least squares problem. So we can't use Gauss-Newton algorithm. It's just a generic nonlinear programming. You could use nonlinear solvers, but it does not possess any interesting structure like Gauss-Newton. So in Gauss-Newton, we work with the Jacobian, we derive the delta x instead of working with the gradient. The advantage of working with the Jacobian was that it gave us the approximation of the Hessian. So we were benefiting from a second order like solver by only calculating the first order derivative, the Jacobian. Whereas if you choose to work with the first order derivative and use a nonlinear solver, we are not benefiting from a second order solver. We are just using a first order solver. It will take more iterations as we showed you with some examples in Julia. So the trick that historically, as far as I know, it was around maybe 70s, 80s, 90s. It was very common 20 years ago to solve a lot of machine learning problems using this technique, is to convert the p-norm to a weighted least squares problem. And the way we do that, by redefining the optimization to be like this. Define your p-norm to be a quadratic term that is weighted. Now, the weighted least squares, if the weights are constant, it is as easy to solve as, or as hard to solve as the least squares problem. That's not a problem. You'll just see a weight matrix in the solution, as we saw it in the regression examples. However, the trick is that we don't want to change the objective function. The weights are defined as to be the diagonally the absolute value of each residual raised to the power of p minus 2. So when you calculate the right-hand side with the given weight, it is still evaluating the p-norm. We have not changed the optimization. However, we trick the solver by alternating between solving a least squares problem and updating the weights. So at the time we solve the problem, we assume the weights are constant. So we solve a least squares problem. Then given the solution, we update the weights. And the next time, the weights will change. So the difference between a weighted least squares problem and IRLS is that the weights are not constant. Hence the name iteratively reweighted least squares. Now, this is a trick to solve the problem. It does not come with any guarantee or any nice theoretical results. It is very practical. It's a practical way of solving a general norm problem.
In the context of robotics, what's an example where we wouldn't use the L2 norm for optimization?
Robust optimization. That's the next example. That's in the context of robotics, we will use this to solve a robust estimation problem. So in practice, you could start from setting the weights to be the identity, solve the least squares problem. That will give you an initial guess, then iterate until hopefully converging to the true solution. Now notice that even if the residual is linear and the norm is not L2 norm, we still need to iterate. So when you initialize, the least squares is of course exact, but we still iterate because we are minimizing a p norm, not L2 norm. So IRLS will iterate even if the residual is linear or affine, because the norm is P norm. Example. So we're going to go back to the same linear regression problem. In this case, the data we have is contaminated with outliers. Outliers are data points that they do not agree with the underlying process that shows the trend. So therefore, they can bias the estimate substantially, because by definition, they are not describing the trend, and then the model that we fit to data can be completely wrong. So dealing with outliers is very important in practice if they exist in data. So the model is not changed. We still have the same n data points. X is a vector, t is the target value or output, is a scalar. We use a linear model, linear in weights with the same Gaussian basis. We still use the first basis to be the bias term. So we do not change any modeling part. However, what we change is the objective function. The objective function, instead of being L2, L2 norm is now L1. L1 norm is traditionally used for solving robust optimization problem. And the reason for that is because L2 is calculating a Euclidean distance and is trying to somewhat interpolate between different lengths, distance between measurements, to come up with some notion of average distance or shortest distance with respect to sum of a squared of terms. Whereas L1 is working with absolute value and taking the straight lines. It's just summing straight lines. It looks like, it's called also Manhattan distance. If you look at New York, all the roads are straight and intersecting and orthogonal. It's type of a distance that it will sum that type of this roads for you. You move exclusively in one direction and then add another direction. It will not try to make a circle like a Euclidean distance. In other words, if you draw L2 norm, that will define, so a 2D ball with norm, L2 norm will be so if the norm is less than some distance, this will be a circle, right? Because we're talking about r being x squared plus y squared. However, if r is absolute value of x plus absolute value of y, this will be very different. We're basically talking about something like this. Now, this is very different. We are not moving in a circle. We're moving along these lines. And that is why when you solve the least squares problem, we need to iterate, even if it's affine. So that's the idea behind L1 norm. And because it's not trying to satisfy both directions at the same time, it tends to ignore outliers in practice. Another property of L1 is that it promotes sparsity. When we regularize the norm of the weight with L1, a lot of weights tend to go to 0. Again, historical reason for that is that when we want to promote sparsity, this is a topic in the sparse coding literature, we want to actually minimize zero norm. The 0 norm is just counting the number of participating weights as opposed to what's the value of the weights. When you raise to the power, right, of 0, the definition of a zero norm is that if W1 exists, it's 1, right? If W2 must be removed, then it's 0, right? Now, however, this is not an easy problem to solve because then we're dealing with binary values. It's not smooth. Because it's difficult to solve, L1 is a proxy for L0 norm. So a lot of times, when you see they add L1 norm as a regularizer to promote the sparsity because it's a proxy for L0 norm. So that's some historical and background idea of why L norm is popping up here as a regularizer. So the objective is, when we assemble everything, minimize the same problem instead with L1 norm. We define the design matrix. How to solve this? This is not least squares. However, we convert the problem to a weighted least squares problem. And we define two new weight matrices based on the instruction in IRLS. The weight matrix must be the diagonal of the residuals raised to the power of p minus 2. P is 1 here, so the power becomes -1. So that when you calculate this line, you get the original objective function. With that, we can differentiate. The gradient will be this term here. Calculate the necessary condition, and the solution will be in this form. Now, only in one iteration, right? Once we find the optimal W, then we have to reevaluate these weights and make them ready for the next iteration. So the next iteration, when we evaluate the new W, this B and G will be different. And that's how we iterate between weights and the decision variable. However, you need to be careful because in the weight matrices, you can see that we have 1 over weights or 1 over the residual. What if the residual is 0? We want to avoid division by 0. So in practice, when you implement, we usually use something like maximum of that positive number and a small number, right? So when it's too small, just use the delta threshold, some small value, to make it numerically stable. Otherwise, you might face all sort of inconsistencies. So another name for L1 norm minimization is least absolute deviation regression. It's robust to outliers, and L1 regularizer term promotes sparsity. There's no guarantee IRLS converges, so we tend to set a maximum number of iterations, and you need to check the solution to see if it's correct or not. So if you look at the example, how in practice I converted these equations into an algorithm, you can see it in this L1 linear regression example. As you can see, a lot of weights are 0. So out of 15 weights, we are only using 5 weights. So 1/3 of weights are non-zeros, 2/3 of weights are zeros. In some sense, it's nice because we are estimating the function using a small number of bases. And that's computationally attractive. As you scale this, Instead of having 50,000 points, maybe you can use 500 points and get a nice approximation of a surface. So it is very attractive computationally. And what would you call these points? Outliers. They are clearly not lying in this simple example, not lying on the true process, which is the blue curve. They are not describing this function. They are outliers. But the solver is ignoring them. Because of the choice of the norm, the way the solver behaves makes it robust. It ignores these outliers. So the choice of the distance or norm can change the behavior of the solver substantially. And these are the survived, we call them survived bases, these circled ones. Now, there are other good ones as well, but the optimizer is recognizing that they're not adding anything. We could get equally good results by just using these 5 weights. So automatically they're being ignored, even though they're good data points. So generalization of this method in the context of Bayesian inference, when you can get also uncertainty for regression, is called relevance vector machine, RVM. RVM is a method that you can do Bayesian regression and classification using these kernels or nonlinear basis, and it is sparse. It behaves similarly. And RVM is a degenerate model compared to Gaussian processes, but it is more scalable. It's degenerate because it's not using the whole data points, and it usually picks a subset of them, and it's not equivalent of GP. But Gaussian processes are more general, but they're not as scalable. So RVM is parametric, assumes this linear model. GP is non-parametric. It's just some side notes.
When we say that RVM is degenerate compared to Gaussian process, would you prefer a model that can describe the data in a more simple expression, so using less weights or less bases, compared to something that may be more robust, but if it doesn't scale, I guess?
Well, Kevin Murphy, in his legendary machine learning book, probabilistic machine learning book, is summarizing this. If you're after speed, go for RVM and scalability. If you're after accuracy and performance, and the problem size is small enough that you can afford more computation, go after GP. That's the bottom line, ignoring all the technical and papers, topics around these two models. Is that a good summary? Yeah. Yes?
I have a question for the outliers. It's not generated from the baseline. It's we add the outliers.
In this case, I added the outliers. But in reality, outliers exist because your sensor, for example, gives you outlier. The fact that the laser beams go through transparent objects, that will give you an outlier. There is a window, and you will hit the window as an obstacle, but the laser is telling you the obstacle maybe is 10 meters away instead of 5 because there's a wall behind the glass. So that's an outlier. And there is no way we know it. If we could detect outliers, and it's possible sometimes, and that's obviously nice, and we get rid of them. But it's just sometimes it's not possible. We need a better, smarter way to not letting them to contaminate the good part of data and corrupt the solution. Robust optimization is one common approach for that. And this is an example of that. There's a question in chat that does the fact that IRLS requires inspection make it useless for autonomous systems? No, because you see endless papers, they're using IRLS, and a lot of time when the setup is nice and we carefully initialize and implement, it tends to work well. However, again, the fact that it does not come with a guarantee, that doesn't mean that we can implement something on the robot like this and assume that it will work out of the box all the time. But a lot of time in practice, it does work. So it's a tool that you want to use based on the problem at hand. It's not a generic guaranteed to work out of box method. So it's still useful. So the next topic is M estimation, and at the end of it, it will get tied back to IRLS. That's how we solve it. So the previous example was just one example of M estimation, L1 norm. There is a general class of robust estimation method, and this is not the only one. There are other methods as well. One very common method in robotics is called M estimation. M stands for maximum likelihood type estimates. So the idea is that we wrap the residual around a kernel, or a norm, if you wish to call it a norm. Sometimes we call it kernel. It's ultimately a function, takes the residual and gives you a scalar, a number. Then this will be the generalization of the maximum likelihood. In the maximum likelihood estimation, this, if L is the objective function and in the context of a statistical estimation is the likelihood function, if you take the negative log of that, that's called maximum likelihood. So that's a very special case of this method. And we will see this in the SLAM. When we define the likelihood, when we see the observation, we define the cost function to be the likelihood, and then we take the negative log of that. Because the noise we assume is Gaussian, the log will cancel the exponential. What we're left with is a least squares problem. However, that might not be the best choice if we're dealing with outliers. So the general idea is that use a robust to outliers kernel instead of L2 norm. Or you can define it this way. You can go back and define the necessary condition using this kernel. This is another way to define it. But in general, we wrap the residual around this new function. Obviously, it's assumed to be monotonically increasing and being nice to optimize, not making the problem to behave widely. It should be continuous, changing monotonically so we can optimize it efficiently. So how does this change the problem? It turns out it's not that difficult. We write down the necessary condition, which says that take the gradient, set it to be 0. Take the derivative of the new objective function with respect to the decision variable, which is now wrapped around the residual, and then again wrapped around another function. Use the chain rule. By chain rule, we know that this will be the partial derivative of the row, the robust kernel, times the usual derivative of the residual. Set this to 0. We use a trick. If you multiply and divide this by the residual, and define this to be your new weight that depends, of course, on the residual, this will be an example of the weighted least squares. Because if your problem is a weighted least squares problem, if you have some weight right? When you take the gradient of course will be the weight times the residual times the partial derivative of the residual with respect to the decision variable. So what we see here is the necessary condition for the weighted least squares problem. There is a problem. The weights are not constant. The weights depend on the residual. If we want to consider it as a complicated function, it won't be nice to solve. So what we do, we use IRLS to solve this. Alternate between updating the weights and solving a least squares problem. And that's the easy way to bypass this difficulty, while we're benefiting from the robustness of this kernel function, rho, to outliers. In general, it's not difficult to see that, as we are doing it here, the weights have this definition. So the weights are partial derivative of the rho function times 1 over residual. So it's very easy to include this in the library. You pick the rho function, the weights are already clear what they need to be. It's just a derivative of the objective function times 1 over the residual. And of course, again, you don't want in practice to divide by 0 when we have 1 over the residual. We need to be careful and mindful of that. So the new problem of M estimation ends up being a weighted least squares problem. The weights are not constant, but we can use IRLS solver to get a solution. So this is a new class of problem. It's a robust least square. And we also learned a way to solve it, which is called IRLS. Let's revisit the L1 norm example. This is another way to formulate it. In this case, instead of L1 minimization, I wrap it around a loss function or robust kernel. You have several choices in libraries and literature. One very popular one and common one is called Cauchy loss function. Cauchy loss function has this form. And this is a scalar. R is a scalar, right? So it takes R, and alpha is just the hyperparameters. It's a parameter you can tune. Its derivative is calculated here. So the weights, we know the weights are like this. So as we iterate, we calculate the residual, and that will give us the new weight. So alpha is a parameter that controls where the loss function behaves sublinearly. If you plot this, you will see something like this. So the original least squares problem, right? It's a quadratic loss function. Outliers, by definition, they have a large residual. They do not agree with the model. So an outlier will have a very large residual. Now there's a big difference if the outlier is here or now suddenly here. It's quadratically increasing the distance. What is the effect of this distance on the gradient? You get a huge gradient that will dominate all the inliers. Inliers, by definition, agree with your model, right? So they don't stand any chance if the gradient of one outlier will dominate them like this. So a robust kernel, what we'll do for you is to bend the size of this quadratic function. Now, there are many ideas. You can truncate it. Maybe you start here. All sort of models, right? You can design this function to be something that in general you want it to behave like this. You want to bend these two sides of the quadratic function so that the outliers are being ignored. They do not have possibly this is the region you consider to be the inlier, right? And it's controlled by this hyperparameter alpha. Then after that, anything will be the same to you. I do not care if the residual has this value, or this value. They're all equally bad. I want to ignore them. So in simple words, that's the idea behind M estimation. Does that make sense to everybody? And this is not the simplified graph. This is because this function rho is taking a scalar, right? You can visualize it. It looks like this. And the residual, although the decision variable can be high dimensional, the residual itself is a quadratic function, right? So the red curve is R squared, or the norm of it, essentially. So we solved the previous problem. Of course, in this case, we are not promoting sparsity. We're going to end up using whatever inlier we have. But as you can see, the outliers are being ignored. However, the weights are all non-zero. So that's also a good way to compare with the L1 solution. We are not aiming for sparsity. We're aiming just for robustness. You could, of course, add the regularizer to make it sparse as well if you wish to have that. So this wraps up the two topics that I want you to learn around the optimization, because you read them in papers, you see them as tools in libraries, and you want to know what does it mean to choose a robust kernel in G2O, for example, or in GTSAM. What does it mean to change that hyperparameter of Cauchy loss to be 2, to be 4? So you know that you're choosing that region to be bigger and smaller. You have an intuition about it. And the examples I gave you are simple enough that you can play with them and build more intuition around them. So the next topic is about extension of these ideas, the nonlinear least squares problem, to Lie groups. What if the decision variable is an element of a Lie group, which is always the case in robotic state estimation problem. We want to estimate a pose. Pose may be in velocity, rotation. It's typically a matrix Lie group element. So if it's not, we know how to do it. By now, if your state is, if you're solving over a bunch of points, or in general, if it's Rn, if it's just position, maybe, we learned how to do it. That's the topic we covered so far. The problem is I want to solve for a rotation or a rigid body transformation, or in general, any of the Lie groups that we discussed. We spent quite some time and learned about filtering. It was somewhat a little more involved because in optimization, we have more freedom because we iterate. The solver tends to be more forgiving for simplifications. Whereas the filtering, you have one shot. You process data, you move forward in time. The more accurate your model is to integrate and move forward, the better results you get. We will never go back in time to correct previous estimates. So the filters are less forgiving because of the lack of looking back at data and reprocessing data. The performance of the invariant EKF as opposed to extended common filter showed us a big difference. So luckily in optimization, things are a little nicer. And we'll see why. A recap of, or recall of Lie groups. You remember Lie group, a matrix Lie group. What was it? Give me a one-line definition of a matrix Lie group. The most general definition.
Closed under an operator. Closed under an operator. Closed under an operator.
Closed under an operator. That's one property of it, but it's not the definition of it, which comes from calling them a group, you're right? If it's a group, it's closed under matrix multiplication. So a matrix group, or matrix Lie group, is a group of invertible matrices that have a smooth operation like matrix multiplication and inversion, as we discussed. For example, so long as you multiply rotation matrices using that closure idea, you always get a rotation matrix, but we cannot add them up. And unlike vectors, now we're dealing with matrices. So you remember that the exponential map was very important to connect Lie algebra, the tangent space at the identity, to an element of the group. It was a series like this, and it does give you the identity for zero vector in the Lie algebra. So we had vector spaces SE3 and SO3 as Lie algebras of SE3 and SO3. We would use the wedge notation, but really any of them is okay. For SO3, you could use cross. This cross notation is also very popular. And the matrix version of skew-symmetric matrix times a vector is equivalent of the cross product. We could define the generators. These are the basis matrices for the Lie algebra. And then we could construct our vector in the Lie algebra using some of these generators multiplied by the coordinates, phi1, phi2, and phi3. Which this time is correct. In one of the lectures, I used the negative of that. Although the negative of it is also a correct basis, it's very confusing because suddenly it makes the clockwise rotation positive. This particular version of basis is what we tend to use because the counterclockwise is positive. So that was a source of confusion. It was not intentional. I just wrote it off the top of my head and used the negative of these matrices. And somebody pointed out that the Lie bracket was not giving G3, but was giving the negative of that because the convention became left hand. So we learned that, let's not go that way. Let's use this version of the basis. So mathematically correct, but physically was too painful to work with it. Now also you know that this corresponds to z, y, x, right? Because if you take the exponential map, this will give you, if I'm writing it correctly, for the negative sign, it will give you something like this. We are rotating about the z-axis. It leaves the z-axis unchanged. For the other ones, it leaves the y and x-axis unchanged. But when we add them together, we consider the simultaneous rotation of these three planes or normal vectors. So we also can write this for SE3. You will have 3 extra generators. And the only difference is that we get the generators for x, y, and z translation. You fill in everything else with 0. Now when you add them, you get your twist. This will be your twist in the form that you are familiar with it. This will be the schiff-symmetric part, and then you get a translation part. And the transformation was the exponential map of this twist. So for every Lie algebra element, there is a group transformation. You have this nice one-to-one correspondences. Ignoring some technicalities for more complicated groups that we're not dealing with them here. We always have this. So this is, we know this much. We want to solve a least squares problem on matrix Lie groups. The problem is that this residual here is a function of multiple decision variables, and maybe one of them is a 3D point, which is not a problem. It's the usual Euclidean decision variable. And then maybe the second one is a pose. Maybe we're also estimating the camera pose, but also a feature that the camera is observing. And that's what SLAM means. Localize and reconstruct the scene, what you observe. And maybe we're also estimating another rotation. Maybe we're also solving for the orientation of an object in the scene. So in this context of optimization, now suddenly there's a lot of potential to solve many decision variables at the same time, whereas in the filtering case, because it gets involved, we tend to aim for a minimal setup that solves a specific problem. This is more scalable in that sense.
Is there a reason why, for example, x1 and 3D point and x3 lie on the same manifold? Should they be on different manifolds, or?
This is an example. There's no reason for. It's not going to be always like this. For example, it will be like this. Any enumeration of different configurations is possible, right? So the domain of the residual will be direct product of a bunch of sets. So in this case, in optimization, a lot of time people think about it as, well, SE3 ultimately is a set of matrices, right? It is a group, but it's a set of matrices. Ignoring the algebraic properties of the group that we use extensively, it's a set of matrices with some condition. And you have a pose, and then maybe you have a point. That will give you a domain for the residual.
Is this going to have different kind of timestamp? Because maybe we're doing the filtering and also smoothing will have different kinds of timestamp, right?
Yeah, the question is, will this have different timestamps? Yes. The optimization formulation is obviously agnostic of that, but when in practice we talk about robotics problem, data comes sequentially in time, and then the trajectory is a discretization of maybe poses at different time steps, and then maybe we want to estimate hundreds of them. So each of them will be one pose independently. And together, we will have maybe 100 poses. So the domain will be very large. 100 poses, maybe 1,000 points, maybe some 10 objects in the scene. You want to estimate their orientation. Anything is possible here. You define the problem. So from the Lie group knowledge that we learned, we immediately recognize that this is not going to work if I just add this delta each time, because as soon as we say that rk plus 1 equals rk plus some delta r, we know that the result might not end up being a valid rotation matrix. These matrices are operating based on matrix multiplication, so we have to respect that. In other words, matrix Lie groups are not closed under addition. We have to multiply. Okay, so that's not a very difficult problem to resolve, but given our knowledge, we are aware of this modification that we have to make. An intuitive idea is that move along the curve on the manifold. In general, if you are optimizing over a surface, right, if your objective function maps points from this surface to some real number, the domain of the decision variable is that surface. There is no use for finding a solution here. That's not good for using it, because, well, every feasible solution must be here on the surface. Now, these Lie groups are like that as well. So there's a set, and we know there are also manifolds, there's surface. The shape might be difficult to discuss, but they are. The main idea is that when you search, move along this geodesics of the surface. Do not go to the ambient environment. The general theorem for this is that your gradient, when you calculate it in the Euclidean sense, you have to project it onto the surface. If you project your gradient onto the surface, in the general case of a Riemannian manifold, that will give you optimization on Riemannian manifolds. So that's a little more general. We're working with a nicer case. It's not any surface, it's a Lie group. For Lie groups, we can use the exponential map. So in general, what that map will be, you have to look into that specific problem. So that makes Lie groups the next nice case for optimization that is more general than Euclidean spaces. If you're interested, I will share more references in this part. There's a very nice book by Professor Baumol, Nicholas Baumol. He's in Princeton. He has a book on optimization on manifolds. It's a very accessible book for engineers. And he has a theorem there that your gradient will be the projection of the usual gradient we calculate in Euclidean space on that surface. In any case, for Lie groups, we use the exponential map, and that will perform that projection for us. That will be the geodesic, as we discussed. That's the best path in matrix groups. So one problem is that we need to calculate the Jacobian for each decision variable by respecting its domain. If it's a point, we linearize it using the usual first-order Taylor expansion, and that will give us the Jacobian, which is the partial derivative of the residual with respect to that decision variable. For example, if your decision variable is on SO3, now to perturb the residual using a delta, we can no longer add a delta. Instead, what we do, we perturb the current point by multiplying the exponential of a delta in the Lie algebra. Does that make sense? This is equivalent of, these two are equivalent when we respect the rules of the respective domain, corresponding domain of the variable. So x, k plus d, this is for Rn. For any Lie group, whether SO3 or SE3, we'll have xk times exponential of d. We don't add, we multiply. Now, why exponential of d? Why not some delta x matrix? Why not? And by the way, this k is in the, I think, yeah, it's here because this is the iteration number. It's not time steps, because you can iterate many times for one time step. There's a difference between index for the iteration number and the time step. We're not talking about the time step here. We're talking about the iteration. So why not like this? Can I just solve for the delta rotation or delta pose instead of exponential of some delta in the Lie algebra? That could be an alternative idea.
Better, and that's why we don't just.
Well, we can capture, in theory, we can capture everything if you just work with the group elements. It's not because it's inferior theoretically. It's completely correct, but there's a reason why we work with the Lie algebra.
Is it because it's better for linearization? Because if we use exponential, we can't linearize it. Yeah.
It is better for linearization. That's very correct. It will make the Jacobian calculations somewhat trivial. You will see the Jacobian calculations are, once we derive it, it's always similar. It's easier in some sense than the nonlinearities in the Euclidean space. However, the main reason is that we want to use linear algebra, and that's the style of Gauss-Newton. We're not going to be able to use it if we're working with nonlinear pose and rotation. That's the same reason in the invariant EKF, we are tracking the covariance in the Lie algebra. Innovation is in the Lie algebra because ultimately it's a vector space and we can use linear algebra to manipulate terms. It will be nonlinear, and we do not know how to have equivalent of those nice calculations on the group directly. So theoretically it's valid, practically it's nowhere as nice as working with the Lie algebra. I do not have an answer how to do it, besides having a generic nonlinear solver. So if it's SE3, same idea. We're just using a different notation to emphasize this is a Jacobian of on a Lie group, not the Euclidean. So typically when you define perturb your Jacobian residual, what we want to do, we want to take the derivative with respect to this perturbed term, d, at 0. That will give a linearization at that point, xk. And what's left is the Jacobian, right? Because the continuous time version of derivation is not moving at delta. It must be exactly at that point in calculus, right? So now I do not expect you to be an expert in linearization and Lie group. This is just to lay out the framework. In future lectures, we have example here, but in future lectures, we want to do this for point cloud registration, we want to do it for RGBD visual odometry, and we want to do it for SLAM. That's how we're going to do it. So this leads to a general framework of how to solve optimization problems on manifold or Lie group. And this narrative is called, framework is called Lift-solve-retract. Lift because it's too hard to solve the problem directly on the manifold. Let's lift it to the tangent space, Lie algebra here. Solve the problem using, let's say, Gauss-Newton or any other optimization method that we know in Euclidean space. Then retract it. Retraction is the integration part, when we want to go back to the manifold using an integration rule. So lift is when we linearize by parameterizing this delta in the Lie algebra. Solve the linearized problem in the Lie algebra. Remember, we're after D. D is in a vector space. For example, it's a twist. And we work with vectorized version of it. It will be an R6 vector, right? So lift, solve the least squares problem. Symbolically, we write it as matrix inversion. But you know at this point that we're not inverting it explicitly. Then retract. When you retract, we integrate. On Lie groups, you know how to integrate using exponential map. If this was Rn, we would just write that's the simple integration in Rn. Now integration, because this is, you can think about it as a kind of differential equation. Let's say x dot equal some v. Use the Euler integration using some delta t time. This will give you xk plus 1 minus xk divided by delta t equals v. Then we will have xk plus 1 equals xk plus v delta t, and then maybe I call, I'm using subscript instead of superscript, but I mean the same thing. Maybe you call this d, some delta. Now in the optimization, we iterate and solve for this delta movement, such that all the objectives, possibly multiple objectives, are satisfied at the same time.
If it is iterative in nature, then do we have to do the Taylor always at d equals to 0?
We always do it at 0. That's also a nice thing in working with Lie groups. We always lift it to the Lie algebra. The delta is always in the Lie algebra, even if we are not at the Lie algebra. Because this is as if I'm writing r exponential of omega, right? Omega, the angular velocity, was in the Lie algebra, in the body frame. But rotation can be anywhere. So the delta movement is in the Lie algebra. But the actual configuration is not necessarily. And because we solve for this delta, we can always linearize at 0. Does that make sense?
Like, why do we linearize it at 0? Like, is it very generic, or does it vary? In other situations it varies, maybe only for.
So the question is, why do we linearize it at 0? And I guess that was the conclusion, that this is integration, right? For Lie groups, you had the equation that we have T dot equals T, this twist, right? And this is called reconstruction equation. You can reconstruct elements of any Lie group using this differential equation, and this is the integration. Now, the question is that why we linearize at 0? Simple answer is that that's how we define the derivative, because derivative is f of x plus h minus f of x as h goes to 0. So if you're going to perturb the function with some delta or h,
Like the step size is 0.
yeah, we want it to vanish. When it's 0, what's the rate of change of my function? So we perturb it with some delta d here, and then when d is 0, we want to see what's the rate of change, which is the Jacobian. So that I think the mathematical reason I can give you is this, that we want the rate of change at exactly the current point, not by moving to a different point. So Arthur is giving another reason why to lift the problem, that possibly the measurements are in the Lie algebra. Physically, that can be a reason too. If you're receiving measurements in the tangent space, maybe that's what you want to do. But as a general framework, this is a generic framework for optimization manifold. Lift to the tangent space, solve, retract. Retraction is when we go back to the manifold. Sometimes this exponential map is called the retraction map or projection map, as if it's projecting from tangent space back to the surface. You can give it all sort of fancy names, but for us, it's ultimately the exponential map. So the Jacobians, unlike what it might appear, tend to be easier to calculate. They are not more difficult. If you practice and then get used to all these matrices that are showing up in a row, then the Jacobian calculation is somewhat simpler because it's very structured. You practice, there are a set of rules, you follow them, you get your linearization. And usually using algebraic manipulation instead of using calculus. One very common way is that use the first order linearization of the exponential map, and that will give you usually the Jacobian. We drop all the higher order terms. What's left is the Jacobian usually. Alternatively, you could define this D to be the sum of individual scalar times their generators, and then you can calculate the Jacobian column by column. We did that for the Euclidean case as well. You could do it here as well, but a lot of time we can directly work with the entire D vector. Sometimes, when you're dealing with a more complicated case, as we will see in the RGBD camera, there is a projection model of the camera, and then there is this transformation inside. So then we use chain rule to take the first part with respect to whatever is coming in. Ultimately, there's a point that is coming to the projection model of the camera. So we take the derivative with respect to that input. And then that transform point possibly depends on the pose. Then we can linearize the second part using these techniques. Vectorization is always possible if you're dealing with matrices. You can vectorize your matrix and calculate them. But I will use a mixture of chain rule and first order approximation, and that will be simpler. But these are general advice on how to compute the Jacobian if you need to.
Excuse me. I have a question for the chain rule and vectorization. For the vectorization, we just put every entry of a matrix onto a vector, or we do the inverse of hedge notation?
We vectorize the matrix because we are taking the derivative with respect to a vector D. Right? Now, in practice, how you do it, you might still go back to independently evaluating each column and vectorizing it. But in general, this is a technique for calculating the derivative of a matrix by vectorizing it. We won't, as far as I remember, we won't use it, but this, if you see it, it's a way of doing it. This is, in particular, very easy to use. So let's see how, in general, we can linearize a residual that is an Lie group, and that will allow us to solve a pose graph problem. That's the SLAM problem, that there are a bunch of poses connected on a graph, and the measurement, the constraints are relative rigid body transformation. It's called pose synchronization, or we call it pose graph. You remember the Baker-Campbell-Hausdorff series. This was a series that was answering this, that answers this question, that if I have X, Y, and Z in the Lie algebra as matrices, if you multiply the exponential of X by exponential of Y, what is the equivalent of this multiplication in terms of one exponential? This answer is not trivial because for matrices, Z is not X plus Y unless XY equals YX. Unless they commute, this is not true. Because if they commute, the bracket will be 0, which is XY minus YX. Obviously, they're both equal, and it will be 0. So, in general, that's not true, and that's the result is famous enough that it's named after 3 people who discovered it. So Z in general will be this infinite series, which you see the first 2 terms are X plus Y. Then you have 1/2 of the bracket. Then you have 1/12 of a nested bracket. Then 1/12 of the nested bracket by flipping the variables. And this nested brackets keep getting deeper and deeper. It's never ending. So it's not very nice to work with. However, it unlocks the answer. That the answer is that we can't directly work in the Lie algebra to capture something like matrix multiplication on the group. Because ultimately, exponential of X times exponential of Y, it's some let's say R1, R2. We're multiplying two matrices, let's say rotation or rigid body transformation. And it's interesting that this will be another rotation matrix. So there is a way to multiply rotation matrices or rigid body transformation without working with them directly in the Lie algebra. So the Lie algebra of a matrix Lie group completely captures the local structure of the group, the algebraic structure of it, at the identity. This is somewhat magical. It's very surprising, and that's what makes Lie groups very powerful. So let's see how this will be useful. By the way, so in general, it's way too complicated. We can't bother to calculate so many terms. We don't have time to evaluate this, and then also we have to iterate as well. And all of that must be very fast. So imagine we could collect all the linear terms. You can write it as, the bracket will be, of course, xy minus yx, right? You just expand it and then collect them somehow into an approximation that is, let's say it will give you x plus what should I call it? I'm going to call it A. Some Jacobian, right, matrix times y. And drop all other terms. Or you could talk about y plus some matrix. In general, is this possible? Probably not. For some groups, it turns out you can do it. And there are papers that, one paper, for SO3 is very easy. We have the results for a long time. For SE3, there's a TRO paper. It was one of the references in the Lie group lecture by Professor Tim Barfoot. He calculated this for SE3 in closed form. Because there's a cross term in the matrix. It's a little long. Nevertheless, we can get the closed form result. And all of these closed form results are available in the textbook. I'll point you out on Piazza to that, in the chapter on Lie groups. So in general, it might not be possible, but for some, numerically, it's always possible. For SO3 and SE3, at least it's possible to do it in closed form. And that's very computationally attractive. So I'm going to summarize what we get out of that. If you remember, we can use the adjoint to shift terms, and we've done it before. If you shift x to move forward, add the adjoint inside the exponential map to be multiplied by the twist. We talked about it in previous lectures. If you're moving it to the left side, add the inverse of the adjoint to the exponential. So using the adjoint, we can shift terms. And otherwise, it's not possible because matrix multiplication is not commutative. And the reason we can do it is just following the definition of the adjoint. Multiply them by x. You get the first one. Turn x to x inverse, and then multiply from left, you get the second one. Because if this is true, this could be x inverse as well, right? If it's true, true for any matrices. X inverse is ultimately another group element. So we could talk about it that way as well. So we know how to shift terms. So the linearization in Lie group is done using BCH formula. We're not using Taylor expansion. That would be a more general way of doing it. But BCH is more Lie algebra friendly version of that. Rule number 1, if both terms are small in the product of two exponential, just drop the higher order terms, approximate it using exponential of sum of them. When you should do that? Well, when both terms are small. If you don't know if they're necessarily going to be small, this is going to be a very rough approximation. You're dropping a lot of other terms that might be large. So this one easy, and this follows from the first two terms of the BCH formula. Now, the actual problem is, what if well, if both terms are big, we're screwed. You can't drop anything. But luckily, that's not the case, because if you remember, when we optimize, we are perturbing using a delta, a d, that is a small. So always one of them is a small. So we're in luck. And when both of them are not small, assuming that in this case the notation KC is a small, and R is your residual that can be large, we are after answering this question. I use the same. What is a first order correction to this R and KC that approximately will give me the product of these exponentials? Following the notation we see below, I'll call it A. I'm going to use A still here. And if we strictly follow the notation, we have to add a hat. So the question is, what is a first order correction to the product of this exponential, as we discussed before? Now take the log from both sides, and then take the v to make it vector, so that you can just also ignore this log and v. It turns out, for Lie groups, it will be the inverse of the right Jacobian, and if the small term is on the right, and the inverse of the left Jacobian if the small term is on the left. Now, left and right Jacobians, there are several ways to derive them and define them, but ultimately, these are the collection of all first order terms in that series, infinite series. And that's how the derivations in the textbook and book goes on. It's possible to derive these matrices. And we do have a closed form formula. I gave it to you on the Lie group slides. For example, for what is the exponential map of SO3? Well, you need to expand these terms and then collect them into terms that show sine and cosine series. And then that's how we find the closed form formula. You can do the same thing here. In fact, the Jacobian for SO3 will have, I'm not going to write left and right. You hold me accountable, but it will have something like this. There's a negative sign difference between left and right. Otherwise, they're similar. Which is a hint to what is my observing frame, right? Am I rotating with respect to a reference, or the reference is rotating with respect to me? Because of these two possibilities, you get this left and right conventions. So it's an integral of that for SO3. It ends up being one integration of the exponential map. But in general, that's something that if you're interested to dig in it, you can learn more, but it is solved for SO3 and SE3 already. We have the results in literature. So if you notice, we linearize, but we always know these formulas. In fact, it could be already available for you as some functions. Although you linearize for different problems, but always the Jacobian is the same. The left and right Jacobians are related using the adjoint. I leave more discussions. If you're interested, we can follow up and look into some of the derivations, but I think for now this is enough to solve our problem. So we just learned a technique to linearize the residual that has a decision variable as on a Lie group. An example that is not computational, consider a residual that is a function of x1 and x2. x1 is a 3D point, x2 is a rotation matrix. The delta that we want to calculate has a d1 term for the point and has a d2 term that we integrate using the exponential map for the rotation part. If we linearize this problem, there will be a Jacobian for d1 and another Jacobian for d2 in the Lie algebra. The Jacobian of the first one is, so we perturb these variables one at a time. And when we perturb the variable with respect to x1 and we differentiate with respect to x1, following the calculus rules, all other variables are treated as constant. So we are not worried about their domain. They're just constant. This will give you the first Jacobian. For the second one, we perturb using d2 and evaluate it at 0. This will give you the second Jacobian. So this was the lifting part. Lift, solve the resulting linearized least squares problem. So the outcome of this part is knowing d1 and d2. Then retract. And the retraction, for each decision variable, follow the rule for the integration. The 3D point, just add it. For the rotation, use the exponential map to integrate. And then iterate until a maximum number of iterations or convergence. So this is a generalization of the least squares problem to Lie groups. Now, something more interesting. This is called postgraph in Islam. There is a sequence of robot poses. There's the initial point, T0, which can be the identity, if that's your initial guess. We move and then we're at this point. How do you get this edge as an SE3 measurement This can come from, for example, visual odometry, point cloud registration using LiDAR, maybe odometry, maybe you have a filter for state estimation. Somehow you can track the pose of the robot. So the measurement here, if you call it Z, is also part of SE3, or you could call it U maybe. T1, the way we track with respect to the world frame. Therefore, T1 is T0 times U. So this relationship exists between these two nodes and the relative pose. You could consider noise as well. But this defines a model that connects these two nodes on the graph. Similarly, we have the same condition here, 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 until T5. Now, these are consecutive links, edges in the graph. They usually come from tracking or odometry. There are non-consecutive edges in the graph. For example, T5 is connected to T3. And T5 is connected to the initial node. In the context of SLAM, we call these loop closures. The loop closures are non-consecutive constraints that connect nodes that are not sequential in time, in the sense that there's exactly the next time step. And they're very important, because without loop closures, there is no way to remove the drift from this tracking. If we only track and connect these edges, there's no way to remove the drift. In practice, this can come from place recognition. For example, computer vision techniques can detect the place, and then once you know that you are revisiting the same place, that means there is an overlap between an image that I see at T5 and the image I saw at T0. Now, using maybe some computer vision techniques and image registration, maybe I get a pose. First, I detect it, and then I establish a geometric constraint. And that constraint, if it's a pose, it will give me a measurement, for example, here, if I call it Z, that is also in SE3. So no matter how I get these edges, it ends up being a graph of poses. So each decision variable is in SE3. My measurements are also in SE3. In general, it doesn't have to be this way, but this is called pose graph, because we only have pose as the variable. Or another name for it is pose synchronization. If you only have rotation, it is rotation synchronization. Then we have, so in this case, we have let's say you could write T5 is T0 times Z. Of course, it's possible, the way you define Z, you could have T0 equals T5 times Z.
So in the implementation for this, is it hard-coded that the pose T5 can, for example, observe T3 and T0? I'm assuming this is not the result of just running Gauss-Newton and these correspondences appearing.
This is a simulation. I am generating the graph myself. So I decided that I want to add these loop closures. In reality, the front end of the SLAM, as we will talk about it, is responsible for constructing this graph. And it's important how you do it, because if these edges are wrong, if they're outliers, then your solver might break down, which is the importance of having an M estimator to some extent ignore wrong edges. It's not going to be perfect. The image processing part, registration part, and tracking part in the front end. Necessarily, in practice, you might add some outliers. Once you construct the graph, this is just an optimization problem that we talk about it. That's the back end of the SLAM. So current SLAM paradigm is front end, back end. Front end is the messy part that processes all the raw data to build this graph. Once you know the graph, it is very principled. You just solve an optimization problem. So GTSAM and G2O are SLAM backend libraries. They solve the graph optimization problem. And they support different residuals and GTSAM they call factors for different measurement models. Whether it's IMU, it's stereo camera, monocular camera, pose, rotation, and so on. So these libraries deal with the back end. You are responsible for processing the front end, the raw data. Successful SLAM libraries like OrbitSLAM, they provide all the pipeline. They take your raw image, they process the front end, they build the graph. OrbitSLAM is using G2O inside for graph optimization. So they do a lot of heavily engineered tasks to solve the problem in a way that it works. It's not perfect, but it is the state of the art in feature-based SLAM because it's very difficult to implement a system like that. That it works. On a lot of data set, it works. And that's why the community value that work so much. So it gives you the front end and the back end. But more on this, we will talk about it more. So this should draw a map that we're talking about the back end and a particular type of back end when the graph is a pose graph. So how to solve this problem? Now you do not need to solve this by hand because you can basically use the GTSAM API or G2 API to implement this. And it will solve it for you. But it's nice to know what's going on deep down. And there's no one way. They might choose different way of approximating, linearizing, but this will clarify how it's done. So the process model for keyframes, these nodes in the graph, we tend to call them keyframes. Because, for example, you add a node to the graph maybe every 1 second, or with some criteria you decide I need to add a node. Whereas between two keyframes, you might have many images, many frames. Out of every 30 images, for example, you get, maybe you just add 1 keyframe. That's why it's not a frame.
How do you determine the keyframe? Is it maybe like the number of unique features between subsequent number of?
Question is, how do you, this is a question for future lectures, but how do you define the keyframe? That's an existential problem. You can set a threshold on time. You don't want to go too far. You can set a threshold on the overlap between detected features you're tracking. You can set a threshold on the magnitude of twist, the delta pose you move, regardless of time. You can set a threshold on the number of features that you lose when you track. Probably you don't want to rely on one, maybe a list of 4, 5, 6 conditions to make sure it's not too soon, because if it's too soon, you're wasting resources. This graph will grow, and then it will make the problem heavier. If it's too slow, you're increasing the chance of failure, because then it makes the problem harder to solve. So that's why most people like to work on the back end. And they write papers on that. And they pretend front end is okay. But front end is not okay. They keep a face in the paper that it was easy to get the graph. So one thing that I find personally attractive, that having something like deep learning for end-to-end processing of something like front end, when you just have too many rules and they're just arbitrary, it's nice. However, deep learning-based front ends at this time tend to be suffering from generalization problem because they can work on particular data sets, but you do need to train them on the domain you use. But eventually it will be nice to have something that is less hand-tuned and more automated. That will make a good combination with this backend. And then how to bring in the learning side to the backend is also ongoing research. You can search a paper, NF ISAM, that's interesting. They are using a normalizing flow, which is a modern Bayesian inference technique, and combining it with ISAM, which is a solver for a SLAM. We'll talk about it in the SLAM lecture. I'm going to clean this. All right, back to the example. So the process model between keyframe J and I, and they are not necessarily successive keyframes, is xj equals xi times ui. If it's noisy, of course, we have this exponential of vk. Notice that this is a time difference equation. It's not a continuous time. So the noise is multiplicative with an exponential now. And as usual, the noise is a zero mean Gaussian in the Lie algebra. Take the log of, so define the residual here to be, by isolating the noise, then we define the residual to be inverse of this function times xj, because it's a matrix. Take the log of this and then vectorize it using v. And the process model, the residual is defined as u inverse times xi inverse times xj. This is supposed to be the identity. When you take the log of it, it's supposed to be 0. That's when the constraint is satisfied. To linearize, perturb, now you can perturb from left or right, and that both are perfectly fine. I'm doing it from the right side, you could do it from the left. Sometimes it's easier from the other side. So perturb xi, all the nonsense you see here, I'm just using the adjoint to shift all the terms to one side and shift this delta to one side, whether left or right. Once you have this, we go back to, remember, this is the residual, right? And this is d, or the delta. Then from here, I know what to do, because now I isolated the residual and the delta term. This looks like the first one, so what I get is the first part, whatever it is, the residual, minus inverse of the right Jacobian, and the residual is this input, times whatever is inside the exponential, which is the adjoint of xj inverse times xi times kc. Now this needs some time, you need to think through it, but this is the result. And the negative here is because of negative here. So I have successfully linearized, and what you see here is my Jacobian. The adjoint is showing up because of shifting terms. Do it for xj in a similar fashion. You get, you don't need to shift terms, so we just get the inverse of the right Jacobian. So it's more principled in some way to linearize residual. And then you will see that I'm solving Gauss-Newton in the code. And take a look, let me know if you have questions. Try to connect it to the derivations. Now this particular problem has more structure. You can solve it using optimization techniques in a global way. And this is the work of Rosen, Carlone, Bandry, and John Leonard from MIT. It's called SE-Sync. This solves the post-synchronization problem up to some noise level. It solves it globally. But this particular work, it's not robust to outliers. So in practice, we still need to have it in a robust way. But this SE-Sync, when it becomes robust, it will be a very nice backend that solves the problem globally optimally. So there's a last example that I quickly go through it and leave it for the point cloud registration lecture. But this is a point cloud registration problem when we want to minimize a distance between two set of points when one of the set, here y, all of them is transformed by rigid body transformation so that it gets aligned with point cloud x. So ultimately, this is a least squares problem, and this notation in this case means when you factorize this covariance weight with Cholesky, you get LL transpose, so the residual has this form. We define this to be R. The goal is to minimize the objective function and find the rigid body transformation. If I want to solve this using Gauss-Newton, I need to find the Jacobian. Once I know the Jacobian, I can just solve the problem. So to find the Jacobian, in this case, it's easier to perturb it from the left side. You can try the right side and see why this is easier. So you can ignore, these are just weights, right? You can ignore L. So perturb the pose and apply a first order approximation of the exponential map. When you do that, you can separate the residual plus this extra term. This extra term, where I define t times y to be just another point z, is showing the Jacobian. So the Jacobian, in the same way we find the H matrix in the invariant EKF, it turns out that if I find a matrix that when I multiply it by C as a vector, it will give me the same result as the left-hand side, that will be the Jacobian. So expand the twist, do all the manipulation, and what you find is this result. We'll go through it in future lectures for different problems again. So we call this Jacobian is 3 by 6, and that's how you can linearize and find the Jacobian. So no calculus, just algebra and first order approximation of the exponential map. So in my opinion, this is so much nicer. So that's it for today.